Okay, I think it's time to start. Can you hear me okay? Yes? So, in this presentation, we will see the sFlow technology. So actually, which kind of problems it solves and which problems it cannot solve. Then we will see how it works. So basically, the agents, the collectors, the way that agents use to communicate with the collectors, the sampling techniques for packets, for counters, and in the last part of this presentation we will see live demonstration of Wireshark and sFlow. So what is sFlow? sFlow basically is a sampling technology that is designed to provide visibility of your network devices as well as of the traffic that is traversing your network devices. And how it can provide this visibility? Well, it uses actually the so-called samples, counter samples and flow samples. Counter samples are used to provide live status and live information on the network devices, including their interfaces, whereas the flow samples are actually designed to provide you the information on the traffic that is traversing your network devices. Those samples are packed into UDP datagrams and sent over the network to the collectors. But let's see a picture. Let's consider this simple network topology to understand the visibility that sFlow is able to provide. Here we have a switch, a router, the internet, and some hosts that are doing traffic. Well, the switch that we can see in the middle of this picture is actually sFlow capable, and it provides us with counter samples and flow samples. With the counter samples, we are able to read the status and the traffic of the switch interfaces, whereas with flow samples, the sFlow is able to provide us information on the packets that are traversing the switch. So let's have a closer look at those samples. This one is the sFlow count. This one is an example of a counter sample. As I said earlier, a counter sample is just a part of an sFlow packet that is put into a UDP datagram. And as we can see in this Wireshark capture, we have a counter sample of sFlow, and we are able to read. This is just an example. So we can read from one interface with interface index 129. We can read if the interface is up or down. We can read the number of bytes that entered the interface. We can read the number of bytes that left the interface, packets, errors, and so on. So these kinds of samples are periodically sent for every interface in the monitored device. The other samples that sFlow provides us are the so-called flow samples. They actually contain randomly selected packets that are traversing your device. So as we can see from this capture, we have a flow sample that contains a real traffic packet sample from the network device. So this is a real traffic packet that has entered the network device at some point in time. And as you can see here, it's a 100% complete packet with Ethernet header, IP. Then there was no room here to show, but we will see later in this presentation that that contain real packets. So, why it's useful sFlow? Which problems it can help us solving? Well, sFlow is useful in general to provide good estimation of the top talkers. Top talkers that can be the top sources or the top destinations of the traffic. But they can also be the top autonomous system, the top conversation, ports, whatever. The top here is important because I mentioned that sFlow is a sampling technology, so it picks random samples of the packets that are traversing the switches. So the higher the volume of traffic, the higher the chance of being sampled for a given conversation. So it's good to do estimation of the top talkers. It's also good, for example, to detect and react to volumetric attacks, such as denial of services or DNS amplifications attacks, because you are able to promptly detect if there is someone that is using your network more to use your network. It's also useful for other tasks, including, for example, the traffic engineering or capacity planning, because you have a live visibility of all your switches and routers interfaces. So you can immediately know if there are interfaces that are underutilized, or if there are other interfaces that are overutilized. So using sFlow, you can understand how the traffic flows in your network, and you can act and react accordingly. You can decide to establish, a new peering on an internet exchange point. You can decide to buy transit from someone. It's also useful to do network topology adjustments. If you have a couple of peers that are talking a lot together, you can decide to put them close in the network, right? Rather than switch, route, switch, route. You can decide to put them close. Or it's useful also for basic network issues, such as faulty interfaces. You can detect interfaces that are flapping up or down, up or down, up or down. You can also detect link congestion. And we will see examples later in this presentation. Well, so sFlow is useful to help us in solving a certain kind of problems, but it's not useful when it comes, for example, to detect the hosts that are talking the least in the network. Because, again, sFlow is a sampling technology. So if one host is almost always silent, the chance to sample its own packets are very low. Similarly, sFlow is not useful when it comes to you can't use that basically to feed intrusion detection and intrusion prevention systems, those that are signature based, because chances to have the signature inside the packet, chances to have the exact signature inside the sample packets are not that high to make this approach useful when it comes to detect intrusions. In addition, it's not useful also to do any kind of stateful protocol analysis. So if you have TCP, forget about doing any kind of retransmissions analysis, any kind of out of order, because you get only a subset of all the packets of a TCP conversation. So it's not meaningful to look at the sequence numbers or to look at the congestion window. It's not meaningful to do this kind of analysis, and it's also not meaningful when it security-wise, it's not meaningful to use sFlow to detect low and slow attacks. So the security attacks that send one packet every minute to cause, for example, denial of service. I can mention the slow loaders attack here, for example. Because low and slow means that they send one packet every minute, so chances to sample that exact packet are low. Finally, again, because you receive only samples, you cannot use sFlow to do content-based network forensics. You cannot extract images or files or sounds from the packets because you only have samples. So let me take this one. It is more up to date. So now that we have seen what is sFlow and why it is useful, let's have a closer look at an sFlow monitoring system. So an sFlow monitoring system is basically composed of two parts. On the one hand, we have the sFlow agents. So those agents are embedded in switches, typically, in high-speed switches. And they create the samples we have seen, and they periodically marshal those samples into UDP datagrams that are sent to the collectors. The collectors, on the other hand, listen for incoming sFlow datagrams and process those datagrams to do the visualization, analysis, alerting, threshold to identify an expected traffic pattern, to do a series of analysis, and we will see some examples in a while. So again, let's use a simple network topology to understand an sFlow monitoring system, how an sFlow monitoring system works. Here you have the switches that are sFlow capable. You have your hosts that are doing traffic. And somewhere in the network you have the sFlow connector. So a piece of software typically that listens for incoming UDP sessions that come from the sFlow agents. And as you can see here, the traffic is unidirectional. The arrow only points to the sFlow connector. We will discuss these more in detail later. So the sFlow agents. The sFlow agents are available in a series of devices and network appliances that are switches, but also routers, firewalls, and network appliances in general. Those are some of the manufacturers. But you can also, but sFlow agents are also implemented in software. So if you want to set up your own sFlow agent on a basic Linux box, on a Raspberry Pi, on an embedded device, just get the open source implementation, you can compile it, and you have an sFlow agent. Of course, this works also in virtualized environments, containers, virtual machines, Docker swarms, and so on. The sFlow collectors. So let's see now some of the sFlow collectors that are available. Some of them are open source, some of them are free, some are paid. Among the simplest sFlow collectors, I would like to mention sFlow Toolkit, which is a very simple command line utility that you can just try it to experience, to do some experiment with sFlow. Among other collectors, I can mention the sFlow Trend Pro, sFlow Trend Pro, that they have a graphical web-based UI that you can see the top conversations or the top interfaces of your network. Another interesting collector is this sFlow RT. sFlow RT collects the incoming sFlow UDP packets, and it's programmable. So basically you can use JavaScript or you can use a REST API to program the collector. This allows you to create custom policies. For example, you can set, you can inject a BGP black hole if you see that there is traffic, that there is an anomalous traffic received via sFlow. Or you can insert metrics in a time series database such as InfluxDB. So it's scriptable. You have a JavaScript engine that you can script to create your own actions depending on the type of traffic that you receive. And as you can see, now we only see sFlow network-wise. So we only see sFlow at the network level or even at the virtual network level. But you can use sFlow also to monitor the applications, to monitor the containers. So it's even more general than what we will see today. Another collector that you can use is known as NTOPNG. We are actually the developer of this one. And basically, it simplifies you the association between the sources of traffic and the physical interfaces that are used by the sources of traffic. So, if you use this collector, you have a list of all the sFlow agents that are in your network, and you can pick them one by one and slice and dice by the sFlow agent, by the output and input interface, so you immediately see in your network who is using and how your interfaces are used. And last but not last is Wireshark, because Wireshark is a very good tool to dissect and inspect the sFlow traffic. We will see a demonstration later. But we also contributed a Lua plugin for Wireshark to actually aggregate sFlow information in order to give you an overview of the status and the traffic of the network interfaces of the sFlow monitored agents, as well as on the top talkers that are currently active on the network interfaces. So now that we have seen the agents, we have seen the collector, it's interesting to spend a few words on the way that the agents communicate with the collector. I've already mentioned that they talk with UDP. So why UDP and not a stateful protocol such as TCP? Well, because first of all, UDP is more memory and CPU savvy with reference to the TCP, for example. And this is fundamental because sFlow runs on gigabit switches with tens or even hundreds of ports. So saving memory and CPU cycles is fundamental because those are really high-speed switches. And it's even more robust when it comes to network congestion because the switches, the agents, don't have to buffer the data for the retransmissions. They don't have to keep the states of using sequence number. So UDP is much more light with reference to a stateful protocol when it comes to monitoring. And the effect of packet loss are negligible because the counters that are sent are cumulative. So if you lose a counter sample, the next sample that you will receive will automatically contain the values of the sample that has been lost. So sFlow uses UDP, but it's not only UDP, but it's monodirectional UDP. It's also known as a push architecture, because the agents unsolicitedly and periodically send the UDP datagrams with the samples to the collectors without being contacted by the collector. So this has a series of benefits. For example, the collector doesn't have to discover new agents, because you set up a new agent, you configure it to export to a given IP address, and you are done. And this also has a reduced workload, both on the collector side and on the agent side, because the collector doesn't have to generate requests or map requests with responses, whereas the agents doesn't have to listen for incoming requests. And this listen is very important, because it is also more secure to have a push architecture. It's more secure because the agent don't have to listen, so that they don't have to have open ports and listen for incoming requests. This is more secure, and it's even more easier to set up and configure firewalls, because the connections, the direction of traffic is monodirectional. And of course, also the latency is reduced, because you don't have to make a request and wait for the response, because you will just receive a constant flow of data. Okay, let's have a look at how the sampling processes work in sFlow. We have seen that the samples generated by sFlow are two, the counter samples and the flow samples. Let's see how sFlow prepares data to actually create those samples. Countersampling. So the countersampling process is the process that actually produces countersamples. Countersamples are produced once every configurable sampling interval. So this is basically what happens. You configure your sFlow agent to export countersamples every delta second. So if those two lines are the input and output bytes of an interface, your sFlow agent will periodically, every delta seconds, will periodically visit the counters, get these values, and put them into an sFlow countersample. The sampling interval, it's interesting to note that the sampling interval is intended only to be the maximum time between two consecutive countersamples. Agents can opportunistically decide to reduce, for example, or even to increase just for 1 second the countersamples frequency. They can do that because they can maybe operate in a period of a reduced load, or they can also get early countersamples to pad other sFlow datagrams that are sent. The other sampling process that is interesting is the packet sampling process. That is the act of the sFlow agent to periodically and randomly sample packets that are entering the switch, that are entering the network device. And it's fundamental to ensure that any packet has the same chance of being sampled. So, of course, we are talking about sampling because it's unfeasible to get all the packets that are entering a gigabit switch with tens or hundreds of ports. But it's interesting to note that even if we are talking about sample traffic, the samples that we receive can be used to quantify in a mathematically provable and in a statistically accurate way can be used to quantify the real volume of unsampled traffic. Let's see an example. Let's consider a simple example with 1 million packets that transit the network, and you have a 1% sampling rate. So this means that only 10,000 packets out of the 1 million reach your hands. So the 10,000 packets are the only packets that we can look at. And we see that among those 10,000 packets, we have 1,000 packets that are HTTP. Well, now, what is interesting is that we would like to know that, given our 10,000 packets, given that we know that 1,000 packets are HTTP, we would like to know the actual number of packets in the original 1 million packets that traversed the network. So what can we say? We can say that in the original 1 million packets, at least 1,000 must be HTTP, because we have seen them in the samples. On the other end, we can find an upper bound for the actual number of HTTP packets, that is 991,000, because we have 10,000 samples, out of which 9,000 are not HTTP. Of course, neither of those values are likely, you know. So it can be proved that the most likely value is the one that maintains the same ratio that we have in the sampled packets. This means that if 1,000 out of the 10,000 packets are HTTP, we have a 10% ratio of HTTP packets. So it can be demonstrated that this 10% holds also in the initial 1 million packets. So the best estimate that we can do is 100,000 in this example. Of course, 100,000 is the best estimate, but it is actually unlikely to have exactly 100,000 packets in the original 1 million. So we can use the statistics and even quantify the accuracy of the measured value that we have. That is, we can say, I know that it's unlikely that 100,000 is the exact value, but I want an interval, possibly narrow interval, so that I can be confident, 95% for example confident, that the actual value falls in this interval. Well, there is a closed formula that you can use to get the bounds of this interval, that in our example, the formula gives us a lower bound of 94,000 packets and an upper bound of 1,500 packets. 105,000 packets. So we can be mathematically and statistically confident that the actual number of packets that have traversed the network, that the actual number of HTTP packets fall within this range with a probability that is 95%. There is another way to read this probability, that is using a percentage of error. Using a percentage of error, we can say, for example, that I am confident that the number of HTTP packets were 100,000 with an error of 6.2%. The interesting thing of this error percentage is this one. So This is the function that shows us the percentage of error. In our example, we have seen that there were 1,000 HTTP samples. And if we look at this line, we get exactly 6.20% as shown in the previous line. Clearly, the higher the number of samples, the lower the probability of error. But the interesting thing to note here is that this function does not depend on the total number of samples. So it only depends on the samples that you have in your hand. It doesn't depend on the total number of frames. It does not depend on the original 1 million bytes. So this means, for example, that you can get the same confidence, you can get the same percentage of error on a small device by configuring a 1% sampling rate. You can get the very same confidence level on an high-speed device that generates 1 million packets per second just by setting up a 0.001% sampling rate. So it's independent on the actual number of frames that traverse the network. Of course, everything that we have seen now is statistically provable, and there are slides at the end of this presentation that present the formulas and demonstrate how to get to these results. So slides will be available. If you're interested in the mathematical background, you can download the slides and see that what I've told you is true. It is not magic.
Who defines it? Is it configurable? What percent?
Yeah, absolutely. We will see later that is configurable. You can say, I want one sample every 100,000. I want one sample every 10,000. It's configurable.
Yes, the counter samples also configurable, and is that separate?
Yeah, you configure the counter samples are cumulative. So, I mean, you configure the interval.
So counter samples are configured by time. And data samples by
correct
by percentage.
Correct. It's interesting now to have a look at other technologies that are similar or not similar to sFlow, but still have been created in the years to provide the network visibility. I'm sure that many of you are familiar, or even they know what is the NetFlow. NetFlow is another technology designed initially by Cisco to provide the network visibility. Then we also have IPFix, SNMP, Harmon. Now, looking at all those technologies, it falls outside the scope of this presentation, but I would like to discuss a couple of minutes maybe with and compare sFlow with SNMP. Because I would say that sFlow is a superset of SNMP. That is, with sFlow you can get the same information that you could get with SNMP with reference to the counter samples. So SNMP gives you the device status and the interface status of your devices. But what you cannot get with SNMP is the flow samples. So using SNMP, you don't know who are the top talkers, who is consuming the bandwidth. This tries to briefly compare the differences of SNMP and sFlow. As we can see, both of them provide us device visibility with counter samples, but only sFlow gives us traffic visibility using the flow samples. The other difference is the architecture, because while sFlow is a push architecture, SNMP is a pull architecture. It means that if you want data from SNMP, you have to query SNMP to get that data.
But does sFlow also give like CPU and utilization?
It can give you both SNMP, and sFlow can give you also CPU and memory utilization of the host, both of them.
You can define which counters you want to export.
Yeah, correct.
Also interface errors and stuff.
Correct.
Is it in the same tube or is it a...
No, they are different samples. I mean, of course, every sample is identified by an ID. And, you know, if that sample has a given ID, it contains that value that can be network interfaces, statistics, or CPU, or whatever.
And they're the same OIDs from the NIP as the...
It's not the same of an OID, of an SNMP OID. It's not the same, but I mean, maybe the semantics is the same. I mean, the eventual target is the same.
So can you tell this is the NetFlow plus SNMP?
It's so sFlow you could tell is SNMP plus traffic visibility. So plus visibility of the packets that are traversing the switches and counters that you have. And SNMP does not provide this, only the counters.
True, but then if you have a choice between the V9 RIPE-FIX and sFlow,
okay,
what would you go?
It's they are different. They are different because sFlow does not do sampling on a per packet basis. sFlow creates flows. So flows are. I have an example of a flow here. Let me see. Okay, this is an example of a flow that can be created by NetFlow. So you have the sources and destination ports that are HTTP and another port, sources and destination addresses. sFlow keeps a stateful representation of all these active flows in memory. So in terms of CPU and in terms of memory, it's much more consuming with reference to sFlow. Because sFlow is stateless. It knows that it has to sample one packet out of 10,000. So it just pick a sample and send it out in a flow sample. sFlow, of course, it's more accurate because it does not sample. It gives you 100% accurate statistics for the traffic to and from any given host, but at the expense of memory and CPU. Because running NetFlow can be really costly, especially in high-speed environment. So it's a trade-off between what you get and what you can actually do. sFlow, it's an interesting approach because we have seen that even if it sends you sample traffic, there is a statistical proof that you can do estimations that are accurate. It's not just sampling that you don't know what was happening with the network. It's sampling, yes, it's not 100% accurate, but still you can quantify the accuracy, and this is mathematically provable.
But is it like a random pick within the range?
It's a random pick. It's random pick. Actually, there are two strategies that you can implement to do the sampling. You could sample, let's say you have a sampling rate of 1,000. You can count until 1,000 and then pick a sample. Count until 1,000. But this is if there is periodic traffic, this simple approach is biased, because if you have periodic traffic, you risk to sample only the same packets if you do this simple approach. So the approach that is recommended is to pick a random number, let's say between, you pick a random number. If it's below a given threshold, you sample the packet, otherwise you don't sample the packet. So this approach is better as it's more robust against synchronized traffic patterns.
Anyway, to add something to this discussion, for a switch there is no option but sFlow. For a router,
For a switch,
sure.
For a switch.
So you cannot really compare them because
like firewalls and stuff, they cannot do SFlow.
I mean, if you have a switch, let's say a 48-port switch, it means that you have a 96 gigabit of traffic to analyze, and this is far too much for such a device. So in sFlow,
It's not too much, as nobody wants to pay the money for the switch that can do this.
no, it's not like that, because then you will end up having to go back all the time. Then you will move them up.
Well, we have to spend the money with the collector, and yes, but it's feasible, but not with a limited budget, I think.
But at least you're available. It's easy, right?
Okay, so I choose an SNMP because I also wanted to show a real example, a real comparison of sFlow and SNMP. So to do this comparison, I used a Ubiquiti Edge Router Lite that supports both SNMP and sFlow. So I set them up together and I started monitoring. I said I want to monitor just one interface. I want to monitor the traffic of one interface, so the input and the output bytes, and I want to see how costly it is to monitor this using SNMP and sFlow. So this is a Wireshark capture of the sFlow traffic generated by my Ubiquiti Edge Router. I created that filter and I said, Wireshark, I want only interface number 3. I want counter samples that are identified by number 2 because flow samples are identified by number 1. And I also said I want just one sample per packet to make sure no other samples have been put by sFlow in the same packet. And I can see here that every packet is 186 bytes. So every of these packets contains all the counters, input bytes, output bytes, input packets, errors, multicast. It contains all those statistics for the interface number 3. And I said, I want to try and get the same information using SNMP. Actually, not the same information, but only a subset of the information I got with sFlow. So I started doing SNMP queries from the command line, and I asked the SNMP, see, at the end of every query there is the .3. That .3 means the interface number 3. Interface number 3, that is the same interface I have configured in this filter here. So I say, I want the input bytes, the output bytes, the input unicast packets, the output unicast packets, and an estimation of the speed of interface number 3. So that, to only retrieve 5 counters, that took 781 bytes. So a quick comparison between SNMP and sFlow shows us that with just 186 bytes we can get all the information that it would have taken 781 bytes with SNMP. And in addition, you also pay the latency with SNMP because you set a GET request and you receive a response after a few milliseconds. GET request, GET response. So it's more savvy when it comes to the bandwidth, this sFlow versus SNMP.
You can have more than one request in single SNMP packet, but...
yeah, you can buy...
So I disagree with this now, but the point is that you don't have to ask for data, it comes...
No, the point is also this, because even if you do bulk requests in SNMP, and they are supported in SNMP V2C maybe, you cannot do a bulk request to get only the interface, only the data for interface number 3. Because bulk requests must be sequential in the MIP of SNMP. So if you only want interface 3, you cannot do a bulk request just to get all these interfaces, because they are not sequential in the MIP.
True, but you can still stuff more than one OID in the GET request, and so you will have more bytes in single, and you will get
so
better efficiency, but you are still You have to request the data and wait. So I see the point, for example, if you are polling devices that are far away, the system can only wait for so many because, well, it takes memory to wait for the data back. So this is not, you are saving the resources on the poller.
That is also.
But how collector is, maybe I'm jumping forward, but with asynchronous arrival of the, so let's look at the interface statistics. With asynchronous arrival of the counters from the interfaces, if you want to make sense, let's say, you want to see what is 5-minute interval statistics, the collector would need to do some magic with the samples to get, I'm getting them in asynchronous method with not well-defined interval. They will arrive at least, no later than X amount of seconds, but they might be coming sooner. Yeah. So you need to collect them and do some math.
Every sFlow packet is timestamped, so you know the clock at the source agent.
And you just need to do calculations.
You can do just calculation at the collector.
Okay.
But SNMP is average, isn't it?
Say it again?
SNMP is a 5-minute interval, it's giving you average of a 5-minute interval.
Here you got the average of the sample.
Yeah. At that, whatever it was, right?
It is still
you have to do the average on your own.
On your own, yeah.
You said all the resources of not
So
possible.
considering it's UDP and it is, being pushed out, does it qualify to be streaming telemetry?
In what sense?
Like how they say SNMP is kind of so expensive and, it's kind of not really practical when you scale it really high.
Yeah.
So they're talking about going to streaming telemetry. Okay.
That sounds awfully similar.
Yeah.
Okay.
Okay, last part of this presentation. Let's see how we can use Wireshark with sFlow traffic. So we can use Wireshark basically in 3 ways: to dissect sFlow packets, to dissect the packets that are contained in the flow samples. So the samples that we have mentioned in this presentation, we can actually use Wireshark to dissect only them, to see what's going on. And finally, we can also use Wireshark as a basic, I would say, collector using our Lua plugin that is open source. I will give you the link later, to see aggregated information on the interfaces and on the top talkers that are using your network devices. So for the demo, I'm going to use the real sFlow traffic coming from 3 switches of an hosting provider in Sweden. So the first example, the first demo that I would like to show is just use Wireshark to dissect sFlow packets, so we can have a closer look at them, see how an sFlow packet is made. To do this example, I could have used the SSH dump extra, but I'm more like a command line guy, so I like to run this command. This command, basically, I'm running a TCP dump remotely on an host, and I created a filter that is port 6343 because I know that sFlow is traversing that host on port 6343. And I'm telling TCP dump, I want the output to standard out, and I pipe the output to the Wireshark standard in to get the sFlow. So, let me open these. Okay, so this is the command. Yeah. And here we are. It is our sFlow traffic. Can you read that? Yes? So those are the sFlow UDP packets that contain counter samples and flow samples. Let's pick one of them. So this Wireshark is telling us that this is in-mon sFlow version number 5. Then we have the agent address, the IP version of the agent address, and the setup time. As I mentioned before, the packets are timestamped. This sFlow packet has only one sample, and it is a flow sample. So I expect to find an IP packet inside that flow sample, and a real IP packet that has been sampled at the switch with IP address, with this IP address.
Question. Go ahead.
It's not a system time, not system time.
Because it's the number of hundreds of seconds since the last time the device rebooted.
And how do you know the time that the device was booted?
You don't know, but you use deltas.
Okay.
So just for delta calculation, so you know the time distance,
Yeah.
because the time travel of the UDP might be different,
Yeah.
so
Yeah.
it is better to know what it was sent.
But the server is sending this, I mean, the switch is sending this, right? It knows what's its outcome. The
What?
switch is sending that number, right? Because it's outcome. When you push last one.
Yeah.
Just on the network. So the IP address of the sender is not retrieved from the UDP header. The IP header it is from the inside. So it means that somebody can be sending in the name of somebody else.
Yeah, you can do that. It's
Okay.
not, I mean, it's not necessary to have the same in the...
Okay.
So, this flow sample actually contain it is telling us that the packet has been sampled from interface with index 8. So we already know the interface, that the packet has entered our switch. We see the sampling rate. You were asking me if it was configured. Here it has been configured to sample one packet out every 1024. You see the sample pool. This is a counter that tells us the number of packets that have been seen. So not just the sample, but all the packets that have been seen since the reset, I would say. This is another indicator that is telling us dropped packets. It means that the sFlow process should have sampled more packets, but it cannot make it, maybe because it's overloaded, and actually because 124 packets is I have told the manager of the switch to increase the sampling rate, because this means it's too low. It means that the switch cannot keep up with the sampling, so it's dropping samples, but at least it's telling us, hey, I'm dropping samples. So this is helpful.
Increase the rate, you mean?
I think it is the other way.
Multiply by 10. There are formulas and suggestions that to configure the sampling rate on the basis of the interface speed.
So they provide a recommendation. There's a recommended.
Yeah, there are recommended sampling rates.
But this is the fixed one.
Oh, you can configure it.
Right, but this one is like we're showing right now is a fixed one. 10.4, 1, random.
No, I don't remember if it's exactly fixed 124 to 1000 or if you can specify an exact number. And here you see raw packet header that I can open up. And here we are, we have Ethernet, IP, TCP, and data.
Actually, packet.
Yeah, it's the
Actual packet.
Yeah, it's the actual packet. It's the actual packet inside the flow sample. See here, you have the tree that starts with mono sFlow, and then you go deep in the tree until you reach the real packet. Let's have a look also at the counter sample packet. So we can do this. Apply as filter. Selected. No. This filter. I say that counter samples are type number 2. Here we are. Here we have our counter samples. So the counter sample, it's pretty similar to the flow sample, but here we have the generic interface counters. Now this interface, I picked one sample of an interface that is down, actually down. So I know that interface, this interface that has a speed, this speed is currently down. Let's see if I can find an interface that is up. It's more interesting. Filter and selected. Over status 1. Okay. So this is an interface that is up. The interface has ID number 6. And here we have all the counters that I mentioned. So the input and output packets, bytes, broadcast, errors, and so on. So inside these counter samples, you could have also have the CPU load, memory, and also other kind of information. Not only network data.
You say you have to configure that. You say
Yeah.
CPU.
So this is basically what we get inside sFlow.
So there are only two types, one for flow and one for SNMP.
There are?
There are only two types of counters, one for flow and one for SNMP.
Yes, one for counter and one for flow, standard by RFC, but they are general, so you can extend them using private enterprise numbers. You can extend them and create your own custom counters. So in the second example, yeah, please.
So flow sampling, like say you put this agent on a 48 port switch, do you have to specify what ports it's doing that on, or is it just do it on all of them, or is it on a per interface basis?
Actually, you can create your own policies. You can run multiple agents on the same switch with different sampling rates, with different monitored interfaces. So you have a complete control over this.
So it's a per interface configuration?
It's a per switch configuration. You can set up multiple running sFlow instances.
So you could have a configuration for all the ports on the switch, or you could do it per
you can say, if you have ports with different speeds, you can specify a higher sampling rate for interfaces that have a lower speed and a lower sampling rate for interfaces that have a higher speed. You have complete control over this. Yeah. So in this second demo, I would like to show you how to feed Wireshark with the sampled packets. So we have seen that sFlow is sending us counter samples and flow samples, and the flow samples contain sampled packets. Now I would like to show you how to feed Wireshark with just those sampled packets. It's pretty easy. Again, we use the same command as before, but I add an extra piece of software in between. This software I mentioned earlier in this presentation is called sFlow tool. So I use sFlow tool to actually peel the sFlow packets to only get the inner samples contained in sFlow. So I'm sending the TCP, the SSH output to standard out, and I'm feeding sFlow tool from standard in, and I'm telling sFlow tool output the packet contained to standard out, and finally I read the standard out of sFlow tool from Wireshark. Okay, so I can close this one. Okay, so this is just the command we have seen. All right. So those packets are the real traffic packets that are traversing the switch of this hosting provider. So we are getting them out of the sFlow and showing them here with the Wireshark. As you can see, there are a lot of black lines. This is basically Wireshark that is trying to apply a color scheme that assumes the packets are not same. So you see a lot of TCP previous segment not captured because there are missing things. But still, there is something that is interesting. Is this one? Let me see if I can show you.
So in the rare occasion, can you say sample 1.1 and give you all the packets? Technically, if you set the count to 1.1, will it give you all the packets?
Yes, in theory, yes. I've never tried to set a one something like that because your network will explode.
Sure, but like I said, it's
maybe in theory, yes.
And I think that it doesn't make it able to do that.
It has not been designed to do this.
Sure, but there's a class.
So there's an interesting thing to know now. See those RST hack that are coming out continuously. We can say, what is the chance of sampling a reset? Under normal conditions, we should not expect to see so many resets in an empty network. So even on sample traffic, I see a lot of resets like this. There's something strange, you see. It seems that someone is trying to brute force some hosts, and they are responding with reset hack. I googled one of those IP addresses, and I found out that actually the IP address was marked as a victim of RDP, of a Windows RDP brute force attack. So see, even with just this screen, I can now call the hosting provider and tell, hey, you have some hosts in your network that are victim of a brute force attack. So the last part, I would like to show you our Lua plugin, our integration. So please go there, download it if you want to try the sFlow plugin. It's open source, you can find it on our GitHub page. And it's basically a Lua tap that registers to Wireshark for sFlow traffic. The plugin gives us basically two new entries in the menu. You have counters and talkers. With the counters, you get See, here we have the agents with their IP addresses, and for the counters we get the input and output bytes and speeds of every interface that is active, as well as the utilization. For the talkers here, we have the top sources and the top destinations that are currently active on this agent. We also see, I will show you the demo now, we don't only have the totals here, we also have the speed that we can compute using the sysub time deltas as before. So let me restart the sFlow feed. Okay. Now I can visit the n-top sFlow counters. Can you see that? So this Wireshark window refreshes automatically as soon as new sFlow packet arrives. See, it updates automatically. So it's a pretty quick way to have an immediate quick overview of the status and load of your sFlow monitored agents. See, for example, you have the input and output traffic for every active interface. You see also the utilization. For example, interface number 25 is utilized at the 37%. So with just this view, you can have an overview, an idea of the load of your interfaces, just by using Wireshark. The other thing is the talkers pane. This pane updates automatically when the new flow samples arrive inside the sFlow packets. We use that samples. We use actually the IP packets contained in the samples to get the top sources and the top destinations with their volumes of traffic that are scaled up using the sampling rate. Because of course, if I receive one packet out of 1,000, I need to scale up the packets by a factor of 1,000 to get the actual values. And those guys refreshes here automatically. We can note that here we see that agent number 2154 has a rate which is in the order of 340 megs. If we look at the talkers of that agents, it seems that they are doing a negligible volume of traffic. So this can be explained due to the drops that we have, because we are actually receiving just a few flow samples, because our switches are dropping almost all the samples they should have generated. So I've already told the network administrator of this hosting provider to increase the sampling rate, because you also alleviate the load and the pressure on the switch.
If you can decrease, increase the number of packets you are looking for, but decrease the rate.
Yes, right. So,
if you don't mind.
Yeah.
The interface number, hopefully it is the same what is the IF index of the SNMP.
Yeah.
Is there, so SNMP has the mechanism to retrieve the target of meaning human readable for what it means.
Yeah.
IPFix has also template that can export it. Does sFlow have something similar?
Yeah, you can.
Okay, so you don't need to rely on other SFlow that deliver everything. Excellent. Thank you.
So, well, time for me to wrap up. Thanks for being here. So, final remarks, sFlow is a pretty lightweight technology that you can use if you want to have an idea, if you want to have a visibility of your network devices and on the traffic that is traversing your network devices. So, just to answer questions like, is my device overloaded? Who is consuming the most bandwidth in my device? You can play with it also with Wireshark. Download our plugin if you want to experiment also Wireshark as an sFlow collector. And yes, feel free to drop us an email or whatever. Thank you.